Quick quiz, chapter 27, current and resistance. Consider positive and negative charges moving horizontally through the four regions shown in figure 27.4. Rank the current in these four regions from highest to lowest. Now, current is the flow of charge. So the more charge that flows, the more current generally. So the first one has 5 charges moving, 3 positives to the right and 2 positives to the left. Now later we'll talk about what's called conventional current, which is essentially positive charges moving, but in reality when current flows it's negative charges moving the other direction. All right, but the net effect, if you had positives moving to the right or negatives moving to the left, would be the same. So since 5 charges are moving in this case, we're going to rank this one as the largest current. The second one has 4 charges moving, and the third one also has 4 charges moving, 2 pluses to the right, 2 negatives to the left, which is like a net of 4 to the right. So these two are going to be equal. They got the same amount of charges moving. Some are to the left and right, but some are plus and some are minus. But both of them have 4. And then the last one has 2 charges moving to the right. We'll call that the least. So the one that has the most charges moving would be the most. Now, if you had both pluses and minuses moving in the same direction, then they would essentially cancel each other out. And that really would never happen either. Question 2. A cylindrical wire has a radius of r and a length L. If both R and L are doubled, does the resistance of the wire increase, decrease, or remain the same? All right, this is in reference to a wire that's like tubular, and its area on there is a circle, so pi r squared. Now the resistance is that rho times the length of it divided by the area of it, and the area of it is the area of a circle, pi r squared. So they're saying this: if both R and L are doubled, so L is going to be twice as big, R will be twice as big, but remember it is squared, so we would have that. Our net effect then is going to be 2 over 4 times bigger, or 1/2 if we reduced it. So by doubling the length and doubling the radius, we're going to decrease the resistance by a factor of 1/4, or 1/2. So a decrease. Question 3, in figure 27.7b, as the applied voltage increases, does the resistance of the diode increase, decrease, or remain the same? So we're talking about the second graph. But first, looking at the first graph here, the slope of this graph is going to be equal to 1 over r. The slope of that graph, 1 over r, because r would be equal to v over I, Ohm's law, and we have y on the y-axis, v on the x-axis, so the reciprocal of it. All right, so the steeper this slope, then the less the resistance would be because of the reciprocal thing. Now in the second graph we have a curve, but we could draw a tangent, and the tangent would have a slope of 1 over r in this case. So as the voltage is increasing, the slope of this graph is increasing, but the slope of the graph is 1 over r, so the resistance is actually decreasing because it's 1 over r on there. So does the resistance of the diode increase, decrease, or remain the same? We're going to say it decreases because the slope is actually the reciprocal of r. So if its slope increases, then r is actually decreasing. All right, question 4. When does an incandescent light bulb carry more current? Immediately after it is turned on and the glow of the metal filament is increasing, or after it's been on for a few milliseconds and the glow is steady? Now remember, we talked about this, how when you first turn on a light bulb, it's cold, the resistance is low, the current is high. So the answer is A. All right, it's a non-ohmic device. When it gets hotter, its resistance increases and the current will be a little bit less. It only takes a few milliseconds for it to reach that steady state. That's why when light bulbs burn out, they usually burn out right when you turn them on, because the filament is worn thin and the momentary rush of current is too much, makes the filament break. Now, question 5. For the two light bulbs shown in figure 2713. Now, this is jumping a little bit ahead because this is a parallel circuit, of which we will talk about a little bit more later. But we have two light bulbs. One is 60, one is 30 watts. If we do P equals V times I, we could do that for both of them. And in a parallel circuit, the voltage is the same for both of them. So V's are both the same. Since P's are different, the one with the larger P power would be the one with the larger amount of current, the 60 watt. It gets more current. All right, now when current comes out of this battery or power supply here, it splits. Some goes through the 60 watt and some goes through the 30 watt. And then when it comes back, it rejoins, so whatever current left the power supply will be equal to the current that comes back into the power supply. So both A and B are the same amount of current, and they are the maximum. C and E are different amount of current, and C would be greater than E. E and F would be the same amount of current, the current going in and coming out of the bulb, and C and D are the same current going in. So the next higher one is going to be C, which will equal D, and then E, which will also equal F. So that's the currents in this. All right, we'll learn about series parallel stuff a little bit more down the road.